So we have obtained the following solution, exact solution of the Einstein equation. du dv plus 2h function of u x perpendicular du squared minus dx perpendicular squared, where h is equal to kappa p delta of u log of modulus of x perpendicular. So now we want to discuss properties of this solution. So consider we want to describe particle geodesics on such a background. Consider a particle, light-like particle, which has a world line so it collides, so to say, with this Penrose parallel plane wave with impact parameter equal to a. So its geodesic has fixed position in this direction equal to a. It means that dx perpendicular is equal to 0. So because it's light-like, this is equal to 0 for the light-like particle, and as a result we obtain the following equation: du dv for such a geodesic, because this path is fixed, du plus dv h of u of a times du. So we have two types of geodesics. One type is du equal to 0, and the other type is dv plus h as a function of u and a times du equals to 0. So these are two types of geodesics. Remember that the world line of this, of the source of this wave is u equals to 0 and x perpendicular equals to 0. So let me draw the picture. So in the direction t, in the plane t and z, we have the following wave traveling with the speed of light. So the world line of this wave is like this. So this is u equal to 0. And this is a slice of x perpendicular equal to 0. X perpendicular equal to 0. So in the direction of x and y is here. Now, if there is a wave which travels parallel to this wave, so somewhere here, it just doesn't feel its presence. So it just goes, this is u constant. U constant. These waves do not feel the presence of the shock wave that we're discussing. But what happens with those which travel along this world line? So that can be described according to this equation. And we have the following situation, that from this equation we obtain that dv is minus kappa p delta of u log of modulus a, because x perpendicular is equal to this, times du. So because of this delta function, before u equal to 0, before this point, the wave travels according to v equals to constant, according to dv equals to 0. dv equals to 0. So it travels like this. No, not the wave, the particle. The geodesic of the light-like particle is like this. Then, at u equals to 0, the particle experiences the shift along the v direction, because integral of this from 0 minus 0 to 0 plus 0 over du integral of this expression of kappa p delta of u log of a is just kappa p log of a. So it carried backwards. So it carried backwards along this direction to this amount. And the distance depends on the value of the impact parameter. Closer in this direction, the particle to the source, longer it is carried. Farther, shorter it is carried. But then it is released and goes again according to this law, but with a shifted v. The v is shifted by this amount. So that's a geodesic for the light-like particle in this shock wave. So the reason for such a behavior can be understood on general grounds. So what we had at the beginning? At the beginning we had a Schwarzschild solution, and for the Schwarzschild solution, the how you call it? The body is spherically symmetric. We have field lines spherically symmetric, basically. Then we boosted with some velocity v, and because of the contraction in the direction of the boost, we basically have field lines more densely compressed in the direction perpendicular to the motion. As v becomes bigger, the density of lines in this direction becomes bigger, and in the extreme limit, as v goes to 1, we obtain such a pancake. So the source is like this, and the field lines are like this. So this picture, while this picture is space-time, this picture is space-like. So which is just time slice, basically, a photo of what is going on. So these are the compression of the field lines. So this is a pancake, the shock wave that we are describing. Now, remember that particle, when it travels, light, when it travels in space-time, which is curved, the light rays are bended. The main source of bending, the main amount of bending happens in the very vicinity of the source, in the very vicinity of the body. So as we shrink these lines, this region becomes smaller and smaller, and as a result here, this bending becomes stronger. And the bending mainly due to the time delay. That is exactly what happens here. We have a time delay when the particle is very close to the crossing the not crossing, but I mean colliding with the shock wave. It is remember that the particle is a distance a away from the source of the shock wave from the source, but it is in the field of the shock wave, and the field of the shock wave is such a pancake. So it experiences time delay and then releases and continues its motion. So these are the properties of the Penrose parallel plane wave. And well, this is a gravitational field. Basically, approximately one can describe by this field the following situation. If you have a brick and accelerated to very big velocities, to such velocities that you cannot ignore its gravitational field, then this is a gravitational field it creates. And if you can consider, for example, collision of such bricks, what they led to, etc., etc. So basically, we have said everything what we can say about gravitational wave. We have studied linearized approximation and small gravitational waves, and also we have studied shock gravitational waves.